Okay guys, this one's going to be on KPIs, or what I mean by KPIs, what that stands for is key performance indicators. I can't come up to a machine and determine what's wrong with it without looking at a number of things. I can't just look at superheat and subcooling and say, you know, we have an airflow problem or a refrigerant problem. You know, I can't just go look at my temperature split inside, my delta T between the return and the supply inside the house, and determine that there's a problem. I have to look at a number of things in order to determine that what my issue is before I can make any kind of definite diagnosis. Okay, so we're going to talk about the most important ones. Dealing with refrigeration now. There's a whole nother list of steps that we'll go through during electrical, to check electrical problems and things like that. So this one's dealing just with the refrigeration side of things. So let me get this thing fired up, let it even out, and we'll start looking at some numbers, and we'll go over what we need to be looking at. Okay, I started this thing up. It's been running for about 15 minutes now. Everything is nice and even and evened out. So let's talk about, when you go on a service call, you go on a no cooling or whatever the call may be, okay? The customer's gonna try, all the times the customer's gonna try to tell you, hey, it just needs refrigerant. This has happened before. Put some Freon in it. That's what they'll say, okay? You're the technician. They called you for a reason. Go be the technician. You need to figure out exactly what's wrong with that thing. You can't just go inside and take an air temperature split and determine that it's low in refrigerant. You can't just go outside and plug your gauges in and look at the suction side, and based on what you see on the suction pressure, determine that you have an airflow problem. You can't make that type of decision off of one thing. So you got to look at all your KPIs, your key performance indicators. Okay, doesn't take very long. You're taking in all the information, and based on the information you get, you can make a better determination of what's going on. Okay. First things you're always going to check when we're dealing with a refrigeration problem. You might suspect it's refrigeration. We're assuming that the system turns on and everything is running, compressor, condenser fan, and inside the house, the blower motor. We're assuming that electrically everything is working, okay? Because we're just talking about the refrigeration right now, okay? First things you're going to check. You're going to throw the gauges on, and you're going to look at your superheat and your subcooling. Superheat is what we're the heat that we're picking up out of the house inside the evaporator. Subcooling, outside in the condenser, we're condensing it back into a liquid. How much are we cooling that liquid down after we condense it? Or subcooling. We've got to look at those numbers. We have to see what they are. We also have to know what type of metering device we have. Okay, right now this is a fixed. I have it written there. Most fixed orifices are going to have a big nut on the outside like that, but visually check. You're going to go in here. You got to check this coil anyway to make sure it's clean. To eliminate that there's any problems there. So just check. Just look inside. A lot of the times the TXV will be hidden in here. It's going to be inside there. It's not going to be, nice and visible on the outside like this one is. This one's just sticking right on the outside. It's not like that most of the time. Most of the time, it's inside here, and you won't know until you physically look. But you gotta know which metering device you're dealing with. We need to know the metering device, because if there is a refrigerant problem, we need to know what we're dealing with metering device-wise, because if it's a fixed, we're gonna concentrate on the superheat. If it's a TXV, we're gonna concentrate on the subcooling when we're charging this thing, okay? So you need to know that. Once we got that determined, okay, we're dealing with a fixed in this situation, okay? Now we're gonna look at our superheat and subcooling, okay? Superheat, our boiling temperature, our saturation temperature in our evaporator. We're dealing with R410A, so we're looking at the pink stripe. If we were dealing with R22, we'd be looking at the green one, and so on. But we're dealing with 410 today. So we're saturating that low pressure liquid vapor mix at 38 degrees, and we're boiling it into vapor at 38. I got my temperature probe on my vapor line. And my top number is that temperature, and it says 39.5. We'll round it up to 40. 40 degrees. The difference between this number and this saturation point is our superheat. We're boiling that liquid in that evaporator, and after we boil it into a vapor, that refrigerant vapor is picking up 2 degrees of superheat. You want to get technical, it's picking up 1.7 degrees of superheat. That's really not a lot. That's going to be my first red flag right there on this machine. It's really going to depend what the outside ambient is, what's happening inside the house. That will really determine what your superheat actually is. But I want to see that somewhere normally in the 10 to 20 range. And at this point we have 2. That's going to be my first red flag. Now I can't just go, oh, we're overcharged based on that one reading. I can't do that, because there could be other things wrong. Don't be that guy. Got to take all your KPIs before you make a determination. That's our first one, superheat. Subcooling. We're condensing that liquid after we compress it. We compress the vapor, the superheated vapor, we compress it. It's a superheated compressed vapor, and it's condensing to a liquid at, let's call it 86. We're condensing that vapor into a liquid at 86 degrees inside this condenser coil. And then after it condenses to a liquid, I want to cool it down. I want to subcool it. So if we're condensing at 86, I'm going to come over here to my liquid line where my other probe, temperature probe, is at. And my bottom number is going to be the temperature on that liquid line. 74.5, rounded up to 75. So I'm running 11 degrees of subcooling, which isn't a ton. You know, you want to be, rule of thumb, if you don't know exactly what your system's supposed to be running, there's a formula to do it, but I always like to say right in the 10 degree of subcooling ballpark. And we're running about 11. Okay? Superheat and subcooling, those are the first 2. So right now, based on those 2, I'm thinking that this unit might be just slightly overcharged. We don't have a whole lot of superheat. We want to be picking up heat. We want to be picking up some heat on this coil in order for us to be cooling the structure down like we're supposed to. So right now the red flag to me, and my meter just turned off, the red flag to me is that low superheat. We have 2 degrees superheat. That's pretty low. Superheat, subcooling, first 2 things you check. Next, I'm going to check the temperature split inside the house. Again, this is a training environment, so I just got this big vent here, but you go up to a vent. You can do it right across the furnace, or right across the evaporator. You can do it that way. I don't like to do it that way because in a real life situation, I like to take my temperatures at the vents. I'll take them at the furnace too, to make sure I got a good temperature split there. But then I like to go into the house and make sure I got roughly the same temperature coming out, maybe a couple degrees more, because we'll lose some in the ductwork. But I don't want to be losing a ton in the ductwork. So if I have a 20 degree split at the evaporator, and I go into the house and I take it at the return and a supply vent, and I only have 15, that means I'm losing 5 degrees somewhere. There's probably a problem with the ductwork. That's why I like to check it in the house. Just another thing I can eliminate of being a problem. Okay? But we want to take in the return air, the temperature we have going in, and the temperature we have coming out. We want to see about 20 degrees difference. So my temperature split on this unit, I got my little probe sticking up in there. That's in the supply. And my meter turned off, let's turn it back on here. It's going to be the bottom number, 51 and a half. Let's just say 52. Bottom number there, 52 degrees coming out that supply. And you normally want to use the same instrument that you used to take the supply. You also want to use to take the return, just to get an accurate reading. But in this case, the thermostat's right here. And, you know, the thermostat isn't as accurate, you know, but it's pretty close. It says 71 degrees in here. So that's my return air. And if I'm running 51, 52, I'm running 19 or 20 degree temperature split. That's pretty good. We want to see about 20 degrees. 20 degrees difference between what we're feeding the furnace, 71 degree room air, and I got 51, 52 degrees coming out my supply vents. 20 degrees difference. Pretty good. So we want to make sure we check that as well. If that's low, if that's lower than, let's say, 17 degrees, if we're getting a 16 or a 15 or a 14 or a 10 degree temperature split, there's something wrong. But we need to, you know, that's another piece of information that we need to have to make our determination of what's going on. Other thing I'm going to check, and a lot of guys forget about this one, is my condensing split. What the hell does that mean? Well, condensing split is the difference between the outside ambient temperature, so the air that the condenser is using to cool the refrigerant down. So the outside temperature. And right now I know we're in a training environment, you know, we're condensing with inside air, but we're going to use that for an example, okay? So I'm condensing at, where my ambient temperature is that bottom number, so 70 degrees. 70, 71, just like what the thermostat says, it's the same air. So it's the difference between the ambient temperature and the temperature we're condensing at, which we're condensing at 86 degrees. So I have a 16 degree condensing split. I have 70 degree ambient air. I'm condensing at 86 degrees. 16 degrees is the difference. I want to see that. Now, a lot of guys will say 30 degrees, and that's true, but it really depends on the age of the system, what SEER rating the system is. The more efficient this system is, the lower that split's going to be. So I like to say, I like to see it between 15 and 30, depending on how old the system is and what SEER rating it is. If we start getting over or under 15, we might start to have, you know, we might be undercharged. There might be some other things. If we're over 30, then yeah, there's some problems going that direction as well. I want to see that condensing split between 15 and 30. Ambient air, so 70 degrees. My condensing temperature, 86, the difference between the two. 16 degree condensing split. I have to know that too, because if my condensing split, if it's 70 degrees outside, and I'm condensing at 110, you know, that's a 40 degree condensing split. Something's going on there. What that's telling me is I'm not getting enough heat transfer. I'm not removing enough heat from this compressed superheated vapor before it condenses into a liquid. I'm trapping the heat in there somehow. That's going to tell me, and that's going to be a domino effect down into the evaporator. The warmer our liquid is, okay, the bigger difference there's going to be when we drop the pressure here, meaning we're going to lose more to flash gas here, which means we're not going to hit this evaporator with as much liquid capacity as we should be. It's all a domino effect. So if I have a high condensing split, I probably have a dirty condensing coil. I'm just not getting enough air across it to cool that refrigerant down as much as I should be. I gotta check that condensing split. So we've talked about superheat, difference between our saturating temperature in our evaporator or our boiling point, and the temperature on the vapor line. We're checking our subcooling, the temperature that we're condensing at in the condenser and the temperature on the liquid line. We're talking about our delta T inside the house, so our return air and our supply air. I want to see a 20-degree difference, roundabout, roughly, right in the ballpark. And our condensing split, ambient temperature, the air that the condenser is using, and my condensing temperature. The difference between the two is our condensing split. The higher that condensing split is, the less heat we're removing from this liquid, this refrigerant in this condenser. The more heat it's retaining, the higher that pressure is going to go. We have to check all of those things, guys, in order to make sure, before we can make a determination that, yeah, it's low on charge, or yeah, it's overcharged, or yeah, there's an airflow problem. We have to check all those things.